Okay, so let's get started with the next talk. My name is Isaac Brodsky. I'm a software engineer at Uber and also work on the H3 project. So I'm going to be talking in a little bit more depth about some of the hierarchical nature of H3. Um, so you heard from Cameron about how we're tiling the world with hexagons and how we're using this in surge pricing at Uber. So I'm going to talk a little bit about um, what were some more reasons that you would want a hierarchical grid system? I'll also be talking about how exactly that looks in the H3 system. So you saw um, in the previous talk that some of those hexagons do not line up when they are subdivided. So we'll look at what that looks like and what are some of the trade-offs that we're making there. And we'll talk about how those trade-offs apply and do not apply to different functions and algorithms that are in the H3 library. So let's get started by talking a little bit about hierarchical grids and what are some reasons that you'd want one. So one early question that you ask when implementing a grid system is what size do you want for the grid cells? And this is roughly how fine of data are you going to get? For let's take an example of somebody walking around a city. You want probably grid cells that are pretty fine, that are able to capture the detail as somebody is walking around. But at the same time, by having very fine grid cells, you're trading off against the storage and computational cost of having a very large number of cells. So you might make a trade-off to use a larger grid cell. This is, of course, addressing the storage and computation cost, and maybe this size, let's say, is appropriate for, instead of a person walking around, maybe a car walking, a car driving around, not walking. But even if we say that this is good for let's say cars, we might have another use case, which is, let's say, planes flying across a continent, and for that, obviously, a different size cell is going to be necessary. So the takeaway here is that different use cases and different data sets may lend themselves to different size grid cells, and you may need to have different resolutions for a grid system. So hierarchical grid systems are one approach to dealing with this problem. And we'll say that a hierarchical grid system is defining finer cells or smaller cells as subdivisions of coarser cells or larger cells. And we also sometimes refer to this using the terminology of child cells and parent cells, child cells being the smaller ones and parent cells being the larger ones. So let's take a look at an example hierarchy, in this case using squares. Squares make a really nice and easy to use example, and we can see how we take some coarse base cell, we subdivide it into 4 cells, and we subdivide that into a further 4 cells. And in this grid system that we've developed here, we have meaningful relationships between these different resolutions. So if we want to, let's say, aggregate data or truncate the precision of our grid cells, we have some kind of meaningful relationship of the cell at the higher level having containment of that cell and so on. Another advantage to having this kind of hierarchical nature, and one that's necessary to support features like truncation and aggregation, like I just mentioned, is having a hierarchical way of addressing cells. So if we take the grid on the far right there, the finest one that we have, I can refer to a specific cell by telling you something like the top row second from the left. So that refers to one of the cells that's in that top left quadrant there. But I can also refer to it by telling you about its subdivision. So I can say in the top left quadrant of the grid, take the top right cell, and that refers to the cell that I've marked as 0, 1, 0 being that first subdivision, and 1 being the subdivision within that. So this allows us to have a tree structure to the grid and allows us to implement all sorts of tree algorithms on top of it and all sorts of data aggregation algorithms on top of that. And in addition to doing this on squares, we can also, of course, implement this on other shapes. So the other shapes that can tile a plane can also be formed into hierarchies with different numbers of cells. For example, we could have a hierarchy of triangles, of squares, of course, and as we're going to talk about in this talk, of hexagons. So moreover than the nature of the grid system, let's talk about just 2 or 3 use cases that we can use this for. One is because we are imposing this tree structure on the grid, we can start implementing tree algorithms on it. So we can start using prefix matching, where we're determining whether or not a cell is inside of a larger containing cell, in this case, without needing to use potentially expensive geometry functions or trigonometric functions. Also, because the different resolutions of the grid are related to each other, are meaningfully related to each other, they have some relation, they are related to each other, we are able to change the precision of data, or change the, I should say, the resolution of data. So this allows us to, for example, take a very high resolution data set and truncate the precision of it, or aggregate it into larger areas. And this can be very useful for computational cost reasons, for visualization reasons. If we need to visualize a large area, we're able to truncate that and move between these resolutions effectively. And it can also be used for this compression use case, as Cameron talked about in the last talk. This is also called compaction in the H3 library. And in this case, we're able to represent a large area using a much larger number of cells around the edges, the areas which there are a lot of detail, and a much fewer number of cells in the center or contiguous areas where there's not a lot of detail. So now that we've talked a little bit about why you would want a hierarchical grid system, let's talk a little bit about what exactly that looks like in H3. And the way that we're going to talk about what it looks like in H3 is by looking at something called an H3 index. And what we mean by H3 index is a reference to a specific cell in the H3 grid system. So what I'm showing here is an output from one of our filter programs in the Uber/H3 GitHub repo. And this is for a cell that contains the 555 market building that we're in now. The H3 index, the identifier for this cell, is the number at the top left there. That's the 85 and so on number. And that number, it's a 64-bit integer, and within it there's a bunch of different bit fields, and we're going to talk about how those bit fields are specifying a specific cell. So the first thing that we start out for every cell is a base cell, and a base cell is one of these 122 coarsest possible cells that H3 can represent. We happen to be kind of roughly in the middle of base cell 20. And then within this base cell, we are subdividing into it. So for the first subdivision, we happen to be taking the center, and the center happens to be referred to with digit 0. And then within that, we're subdividing within it, and subdividing within it, and so on, up to the resolution of this specific H3 index. And once we perform all those subdivisions, we find a specific cell that this H3 index is representing, which happens to be part of the San Francisco Bay Area. So as we're making these subdivisions, a question is, what are the possible digit options? We're subdividing hexagons into 7 smaller hexagons, into 7 finer hexagons. And that looks like this for the cell that we're using as an example. And this works okay, but a problem with this, a trade-off with this, is that this shape is not actually a hexagon. It kind of looks hexagonal, but it has these jagged edges, so clearly it has more than 6 edges. It's not a hexagon. This is where the trade-off comes in with using hexagon subdivision. When we subdivide the hexagons in this manner with Aperture 7, this is introducing shape error. So you can see in this example, when we subdivide from this coarser cell into finer cells, those finer cells are only approximately contained within the coarser cell. So they are at the edges, partially inside of and partially outside of that coarser cell. And this introduces a fixed amount of shape error at every subdivision in the H3 grid system. Also, what's happening here is that the orientation of the grid system is changing back and forth. So every time it's subdivided, the grid is changing orientation by about 19 degrees, and that changes back and forth at each resolution. So we also mentioned in the last talk that we need to introduce pentagons into the grid system. And pentagons are necessary in order to make H3 a fully global system. We couldn't tile an icosahedron with only hexagons. We need to introduce these pentagons, and specifically we need to have 12 of them. Pentagons really differ from hexagons in the H3 system by their hierarchical properties. And by that, what I mean is a pentagon is the same as another H3 cells, another H3 index. The difference being that one of the finer cells has been removed from it. So in the pentagon case, there are 6 finer cells, of which 5 are hexagons, and 1 is another pentagon, which is the next the pentagon at the next resolution, since every resolution is required to have these pentagonal cells. So now that we've seen a little bit about what that subdivision, what that hierarchy looks like in H3, let's talk about some different algorithms and functions in the H3 library and how this does or does not affect them. So the first function that I'd like to talk about is the indexing function, or what we call. And this is also referred to in code as geo to H3. And this is the function that's taking some coordinates and a resolution. And it's giving us the identifier for the cell that contains that point. So in this example, I have a point and I have some resolution of the grid, and I've asked to see the cell that contains that point. So we mentioned there's this shape distortion, but the shape distortion does not apply to this function. If I move the point even a little bit, and I don't know if that's exactly in the parent cell or not of this cell, that indexing operation is still exact for the resolution that I've specified. So the takeaway here is that indexing is exact at a specific resolution. Because we're giving it a specific resolution to work at, it's able to apply that resolution's grid exactly to indexing this point. An example of a case, though, where we do have this shape distortion is in truncating the precision of an index. So in this case example, what I'm doing is I'm taking a point, I'm indexing that, I'm finding the cell that contains it, and I find some cell containing it. And then what I'd like to do is I'd like to truncate the precision of that cell. I'd like to make a larger cell that contains this. And when I do that, what I find is actually that this containing cell, it contains most of the cell that had the point, but does not actually contain the point. And this is where the shape error comes into play in the H3 library. When moving between differing resolutions of the H3 grid, this shape error comes into play and will distort the shapes as it's happening. Let's come back to the compression use case that we talked about earlier, where we're taking a dense set of cells and we're using a smaller set of cells, the smallest we can, to represent that same area. This is called compaction inside of the H3 library. In this case, we compact it. Because we're changing the resolutions of the cells, we are introducing that shape error. So when we compact a set of cell identifiers, the compacted set does not exactly match the shape of the original set. However, this is a lossless compression mechanism, so we are able to uncompact it to the original resolution that was at. And that is giving us the same set of cell identifiers that we had originally, so there is no shape error that's introduced when uncompacting it. However, there is shape error when the compaction, so that does mean that the compact representation is not representing exactly the same area. So you can, of course, learn more about different functions in the H3 library, and we're always, of course, welcoming contributions and pull requests to our documentation, and you can find that on GitHub at uber.github.io/H3. And to summarize some of the things that we were talking about, H3 is a hierarchical grid system. So there are different resolutions of the H3 grid. There are 16 of them. And there are meaningful relationships between these different resolutions. They're built as subdivisions of the coarser resolution. These subdivisions do have shape error, but some functions that are operating at specific grid resolutions or finding neighboring cells, things like this, are not affected by the shape error. Functions that do move between resolutions in H3 are affected by shape error. There is this fixed margin of error that is happening, and that does cause shape distortion. And so it's important to be aware of that when implementing systems on top of H3. You can, of course, learn more again at our GitHub, and we're also happy to answer questions. Thank you.